going through early atomic theory. We're going to put all this together into really getting a feel for atomic theory and the structure of atoms, and we'll even take structure and relate it to function. Partway through this, once we start writing electron configurations, there's an embedded video that's going to take some time to watch, and I'll let you know when the time is right to go through that. When we're done with this, you should be able to do homeworks 5 and 6. Actually, partway through, you'll be able to do homework 5. I'm going to break this up into a couple of videos. I'm not exactly sure where I'm going to stop, but we'll just go until we go and stop when we have to stop. All right. So, where we had left our heroes after the last set of slides, we know that the atom has protons with a mass of 1, a charge of 1 in the nucleus, neutrons with a mass of 1, a charge of 0, also in the nucleus. We got the idea of the nucleus, if you recall, from the gold foil experiment. All right, and then electrons we know are very far away from the nucleus. We know they have a negligible mass and a charge of -1, and from atomic spectra and the fact that the lines are discrete, we know that there are discrete energy levels that they can exist in. However, if we want to look at behavior, we saw a long time ago, just with the potassium stuff early on, that if you change the number of electrons, the behavior changes significantly. And remember, for atoms to react, they have to bump into each other. When they bump into each other, what's going to hit? The outsides, and what's on the outside? The electrons. So we would like to have more detail. Now, why can't we just look at them under a really powerful microscope? Well, first of all, it doesn't exist. Secondly, it can't exist. And the reason is, think about how a microscope works, right? It's light. Light bounces off of things and hits you. That's how you can see it. Well, we already saw from the photoelectric effect that light can move electrons. So that would mean measuring them would move them. That concept is called Heisenberg's uncertainty principle, and it's a little bit more detailed than that, but for the purposes of Chem 152, it says you cannot know both the position and the momentum of an electron, and that's because measurement of one would change the other. Now, position is obvious, that's where something is. Momentum is not only how fast it's going, but which way. So momentum is the product of the mass and the velocity. The velocity, remember, is not only speed but direction. So you can't know both where it is and where it's going, which means that you cannot treat it as a particle. And we talked about an electron as a subatomic particle. So it looks like we're in trouble because we're talking about subatomic particles. We can't treat it as a particle. However, and I do want you to remember the name of this, Heisenberg's uncertainty principle, because that's the name of it. And what it tells us is we cannot treat the electron as a particle. So this is what it's called, this is what it is, this is what it means. Now, if you recall a long time ago, in one of the second lecture, I want to say, when we talked about the law of conservation of matter and energy, remember, matter and energy can interconvert, and it suggests that perhaps maybe they're not different things, but different ways of looking at the same thing. Remember that? Yeah, like it was yesterday. That comes from what's referred to as the wave-particle duality of nature, which basically says particles have wave properties, or matter is energy, and waves have particle properties, energy is matter. Meaning you can treat matter as energy, you can treat energy as matter, which means we could treat an electron as either a wave or a particle. It's kind of in the middle. So we put this together. So we could treat an electron as a wave, energy, or particle, okay, matter. So we put these together. The wave-particle duality says we can treat an electron as a wave or a particle. Heisenberg says you can't treat it as a particle, however. So, you guessed it, in the modern model of the atom, an electron is treated as a wave. Okay, I like to say, actually I had a student once write on a test, it's a wavicle. So the idea of the wave-particle duality is that there's waves and there's particles, but there's this gray area in between. The electron is really in the gray area in between. For the model of the atom, we treat it as a wave. Right? Also, I didn't say this at the beginning, but of course, for all of these slides, all the videos, you should be having the slides on in parallel so that you can hit pause if you need to go back and forth amongst the slides. Okay, so the bottom line, you take Heisenberg's uncertainty and the wave-particle duality. This says we can treat it as a wave. This says we have to treat it as a wave. So the modern model of the atom, an electron is treated as a wave. Now, specifically, it's treated as a standing wave. And a standing wave is if you were to say pluck a guitar string or something, the wave actually is going this way. It's moving, say, from here, but it looks like it's just going up and down, and that's because waves will interfere with themselves. So the wave will go up and back and up and back, and it'll interfere, and if you get the frequency right, you get an interference pattern that looks like this. And these spots where there's no energy, this is a node, and you can get all sorts of different patterns. And a node is where the wave energy cancels out. If you've ever been on your cell phone and you stand in a spot and all of a sudden the cell phone cuts out, that means you're standing at a node. Remember, cell phones run on radio frequency. Okay, so this also says how can the wave be here and never be here? And that's because here it's a node. So taking all this stuff together, Erwin Schrödinger came up with an equation, and he combined several things, combined charge-charge interactions, equations for standing waves, some statistical stuff, and came up with an equation. The solutions are called quantum numbers. You'll deal more specifically with quantum numbers in Chem 200. But what they describe are regions of space where the electron is. These are called orbitals. And they're really probability density regions, like 90% confidence intervals for those of you who are taking some stats. They're called orbitals. So the orbital isn't exactly where the electron is, it's where it's likely is, but we just kind of treat the orbital as if it's the electron. So it kind of looks like this. All right, so yes, it can be way out here, but in general, it spends most of its time here. So it's a good idea to think of it that the electron is the orbital. So where is the electron in the orbital? It's everywhere. Think of a particle moving at light speed. It's everywhere at the same time. And I like to say that it's an electron cloud. It's a negatively charged cloud. And you could say that the orbital is the electron. And it's kind of nebulous, but it works. Okay, so I said this already. All right, now let's start putting this stuff together into something that we can use. Okay, so recall energy levels from before. In the quantum mechanical model, energy levels are numbered. That's what's called the principal quantum number. And they're numbered just 1, 2, 3, 4, 5. And so if n equals 1, it's the first energy level. N equals 2, it's the second energy level. Again, if you need to review the previous slides, what we mean by energy levels, feel free to do so. All right, now, within energy levels, there are one or more what are called sublevels. These also come from quantum numbers, and they're called S, P, D, and F. These are pictures of them. They're graphs of the wave equation, and this is energy increasing, so F orbitals have more energy than D. Right? And you do not need to memorize the shapes, but it's kind of nice to know. And again, how can an electron be here and here, never be here? It's a node. All these areas where there's nothing, those are nodes. And then the sublevels are broken up into what are called degenerate orbitals. So orbitals within a sublevel have the same energy. So that means all 7 of these F orbitals have the same energy. All 5 of the Ds have the same energy. And S sublevel has 1 orbital, P sublevel has 3 orbitals, D sublevel has 5 orbitals, F sublevel has 7. The language is really important. You need to remember energy level, okay, 1, 2, 3, 4, 5, and so on, sublevel, S, P, D, and F, and then the orbitals within the sublevels. So there are 5 orbitals within a D sublevel. Okay, you want to think of it that way, like floors on a hotel or something. So just to summarize it, not every sublevel is found in every energy level. So the first energy level only has the S. Now what we're going to is a notation that we're going to use. So the notation is an addressing system to explain where the electrons are for any atom. So the notation for an electron in the S sublevel on the first energy level is called 1s. For the second energy level, there are S's and P's, and so there's the 2s and the 2p. So this is the S sublevel on the second energy level. For 3, there are S, P, D, and F, and these are the notations. So the 3D means the D sublevel on the third energy level. And starting with 4, they all exist. So if there's 4s, 4p, 4d, 4l. All of those exist. Now, technically, theoretically, there's more than S, P, D, and F, but we don't deal with those in real life, so we're not going to worry about them. Now, it turns out when you do the math that you can have 2 electrons in the same orbital. So any one of these well, any one of the orbitals can have 2 electrons, but they have to have a unique address. And so each electron in an atom will spin on its axis. What's called the Pauli exclusion principle says that no 2 electrons can have the same address, can't be in the same place at the same time. And so they have opposite spins. So one spinning up clockwise, one spinning counterclockwise. We typically represent it with arrows. So any orbital can hold a maximum of 2 electrons. Therefore, and if there's 2 electrons in an orbital, they have opposite spins. So this is a summary. An S sublevel has 1 orbital, that means there's 2 electrons. P sublevel has 3 different orbitals, that means that each of them can hold 2, so there's a maximum of 6 electrons in a P sublevel. The D sublevel, there are 5 sublevels, so just remember the odd numbers, and then times 2. And F has 7 sublevels, 7 orbitals, each of them can hold 2. Right, at this point, you should be able to do homework 5, so I'm going to stop this video here, and we'll pick up with the next video after this. So this would be a good time you can do. I've even put homework 5 after the first video.